morning, everybody. My name is Battista Biggio, and I am an assistant professor at the University of Cagliari in Italy, and also a co-founder of Pluribus One, which is a spin-off company of our university laboratory developing cybersecurity solutions based on machine learning. So today I'm going to talk about wild patterns, 10 years after the rise of adversarial machine learning, which is the title of one survey paper I co-authored with Professor Fabio Roli from our lab. And basically this is a talk inspired from the tutorial we gave at several conference venues. Of course, now it's squeezed to more or less cover everything with also sort of a new twist within an hour. You can find some more details about previous editions of these talks and tutorials at the URL that you see on the slide. And let me also take the opportunity to thank all the organizers for this distinguished lecture series and for having me here today. So I'm sure all of you have heard about AI being the new electricity driving the innovation of businesses and industry in this century, as electricity did a century ago. And we have seen unprecedented success in many different applications, ranging from cybersecurity, robotics, healthcare, speech recognition, and virtual assistants, for example. We have nowadays cars that can recognize other objects while driving, such as other cars, pedestrians, traffic signs, and so on and so forth. We can talk with our preferred voice and virtual assistant, and we have many other breakthroughs in which AI is used as the main tool driving innovation. So on the one hand, we have all these nice technical advancements for the field, but on the other hand, all these new algorithms expose new risks to security. And we have seen a number of attacks in recent years directly targeted to AI algorithms. We have, for example, here these authors from UC Berkeley. They've shown that an attacker may craft adversarial stickers that can be placed on traffic signs, for example, as you can see on the left on this stop sign with the stickers, to basically confound the recognition algorithm that you may have on board of your car. And now, as you see that the car is approaching the stop sign on the left side, you see that it's correct. It's misclassifying the stop sign as a speed limit, while on the right hand side the prediction is still correct. And this happens consistently throughout most of the frames, or almost all the frames that you can see in the image. Other examples include the construction of adversarial eyeglass frames, like the ones that you see here in the picture. And when they are worn by this gentleman here, who is one of the authors of this study, well, the algorithm, which is meant to do face recognition and based on deep learning, thinks that this gentleman here is instead Mila Jovovich, who is a very famous Hollywood actress. And that's again another example of how to deceive these systems in the real world as well. In our group, we did some similar work attacking the robot vision system of iCub, which is a humanoid robot developed by the Italian Institute of Technology. And this system again uses deep learning to recognize objects. So what we've shown is that you can actually fabricate small stickers that an attacker may place on some objects to have them misclassified. And as you see from the demo, what you notice is that regardless of their position, putting these stickers on an object allows the object to be misclassified as another one. And depending on the color pattern that you use, you can have a misclassification in a different class, essentially. We have also examples outside of the image domain, of the image classification domain, for example, in the audio domain, where Nicolas Carlini and David Wagner have shown that one can essentially perturb the input audio to one system to deceive speech-to-text transcription. And here we have a clear example. So I'm going to play a clean audio signal, and then you'll see how Mozilla Deep Speech transcribes the text.
Without the dataset, the article is useless.
So in this case, that's the transcription of the sentence we have just heard. And now I'm going to play a manipulated audio, which only has a small imperceptible sound in the background, and you'll see how it is instead transcribed by the same algorithm.
Without the dataset, the article is useless.
So the second signal is transcribed as, "Okay, Google, browse to evil.com." And we have many different examples. So essentially, the attacker can almost completely control the kind of sentence which is transcribed by the targeted algorithm. So now that we have more or less enumerated these threats and examples, we try to answer to the question about how they work. So the basic intuition behind how these attacks work is to actually reverse the learning process. So exploit a mechanism which is similar to the learning process used by machine learning algorithms. So we know that to train machine learning algorithms, at least in the supervised setting, which is the most successful one up to these recent days, we need a large collection of labeled data sets, labeled data, and then we can train our preferred classifier, for example a neural network, by essentially minimizing the amount of errors that this network does, or this classifier does, in predicting the training samples. How is this error minimized? Well, you choose one of your preferred loss functions, which is basically a proxy measure to the error, and then you iteratively manipulate update the network weights or the classifier parameters to reduce this error. And this can be achieved by essentially updating the classifier parameters along the gradient direction, so by following the derivative of the loss function with respect to the weights or the parameters. Now for the attacks, the idea is essentially the same, except for the fact that instead of minimizing a loss function, you actually want to increase the error, so you maximize the loss function that you consider, but you do that with respect to the input data rather than with respect to the classifier parameters. And this was basically the idea that we exploited back in 2012 and 2013 to break some machine learning algorithms, in particular SVMs and neural networks, and then that then became popular after the work by Christian Szegedy and Jan Goodfellow, showing the same vulnerability on deep learning algorithms. But we will see later on how, let's say, these two independent discoveries led to basically the same algorithms. So the rough idea of these attacks is that you can take, again, the derivative of your loss function, so the one that will basically, if you increase it, it will cause a misclassification. And if you take this derivative with respect to the input sample, so specifically for images with respect to the input pixels, you get this strange perturbation pattern, which is the gradient of the error function. And then, since you want to maximize it, you sum this perturbation onto to the original image, and what you have is a slightly perturbed image, which is now misclassified as another class. So in the specific example here, we have the image of a parrot, which is misclassified as bookcase. And so the underlying, this is all to say that the underlying idea of attacks is the same of the learning process. So you exploit the same tricks from mathematical optimization to actually maximize an error function rather than minimizing it. So that's the basic idea. And now let's go back back in time for a while to explain how we add this idea of optimizing attacks against machine learning, and then I will tell you how Szegedy and Goodfellow come to the same idea by following a different path. So by the time we started, I started working on this field at around 2006, 2007, but the very first work on adversarial classification dates back to 2004. We will mention it later on, but let's say between 2004 and 2012, the main focus was on studying the security of machine learning in the context of cybersecurity tasks. And in particular here, the idea was to try to bypass spam filters and other simple malware detectors. But let's start from the spam filtering case to have a concrete example. And in particular, if you consider spam filters, they are based on, so they have a text classification. They use text classification and they use linear classifiers for text classification. These classifiers are very simple. So if you consider a realistic feature representation in which each word, so each email is mapped onto a vector space where each dimension is a Boolean value corresponding to a given word. So 0 if the word is not present in your spam, or M email, 1 if it's present. So as you see here, you may have an email where some of the words are known to the system, like start, bank, portfolio, and so on and so forth, the red highlighted words, and you see that the corresponding feature values are set to 1. So the X value corresponding to those features is set to 1. Now, how does a linear classifier work? Well, it's just during training, it just learns a set of weights, and you can assume that it will learn positive weights for malicious words, namely words that appear in spam more often than they do in ham emails or legitimate emails, and the same holds for benign words or legitimate words. They appear more often in legitimate emails, but not quite frequently in spam. So now that you have your words and weights, you can compute a score, the output of the classifier on each given testing sample. So let's assume you have this email as input, and now you find this these words highlighted in red in the text, and you have your weights, the weights of your classifier. So what you do to compute the score, what the linear classifier does is just sum up the weights that correspond to the present features. Okay, so in this case, you sum up the weight of start with bank, portfolio, and so on and so forth. And if you sum these weights, what you get is +6. Assuming that you have a threshold of 0 and positive means spam, here you have that your input email is correctly classified as spam. And now, what if you play the role of the attacker and of the spammer and you want to bypass this spam filter? Well, what you can do is try to lower this score by, for example, manipulating or misspelling some bad words in a way that they are still understandable to humans. For example, if you change the A in start and bang, you got some similar text, which we as humans can understand. We can understand the meaning, but now the machine is no longer able to detect these words in the email, and so the corresponding feature values will be set to 0. And similarly, the attacker can also try to guess some of the good words used and learned by your filter. And so if you apply these changes to your input spam, what you have is that now, and you recompute the score now, you have successfully decreased the score below the threshold of 0, and so the email is correctly classified. And now, between 2004 and 2012, this was fairly easy because, you know, linear classifiers have a clear interpretation. So you have a weight assigned to each feature, and then you know how to it's easy to understand how to manipulate the input data to mislead detection. But what happens if the classifier is not linear? And in particular, if you have, you know, an arbitrarily complicated function where the relationship between the features and the classifier parameters is not clear. Okay. Well, in that case, it was not clear at that time what an attacker could do to bypass detection, up to the point that some papers appearing in top-tier security conferences were claiming that more complex algorithms, more complex classification algorithms seem to be more secure. In particular, in the context of detecting malicious PDF files, in this paper, the authors wrote that they were trying to attack a nonlinear SVM classifier with the RBF kernel, so with the Gaussian kernel, And what they found was that while they were able to bypass a linear classifier, their heuristic attack against a nonlinear classifier was not able to bypass it, was not able to evade detection. And they conclude that this was due to the fact that the classifier, this specific nonlinear classifier, is more robust thanks to the nonlinear transformation that it applies, okay, thanks to its complexity in a sense. And so this sounded a bit suspicious to me at that time, and I was collaborating with Nedim Sherndich and Pavel Laskov, the authors of this study. So we shared a little bit of thought about this, and we came up with the idea of basically cast the problem of attacking nonlinear classifiers as an optimization problem. And again, if you go back to the spam filtering case, what was the goal there? The goal was to take a positive score, so a sample which is classified as malicious, and now decrease this score in a way that the score crosses the threshold, goes below the threshold, and the sample is classified as legitimate. And then we wrote this down. So the idea is you have to minimize the classifier output, assuming that positive is malicious, and you want to have malicious objects misclassified as legitimate. And you minimize this output with respect to the input data, subject to some constraints, some feasibility constraints for the attack. So in the case of emails, you can say the attacker cannot modify more than epsilon words, or in the case of PDF, you cannot inject more than a given number of objects, and so on and so forth. And this parameter here, epsilon, will be something that you can, is a hyperparameter that you can vary in your evaluation to check how the behavior of the classifier changes as the attack is increasing its strength, in a sense. We will see some evaluations later, but that was the main idea. And recall that all this adversarial machine learning area makes sense only because the attacker is bounded. Because if the attacker was unbounded, we would have no chance. So the attacker will always win. So in this case, everything makes sense because the attacker is bounded. And now that you look, once we wrote the problem as an optimization problem, you can recognize that there are many tools that you can use to solve this problem. And since most of the learning algorithms are differentiable because they use this property for training, what it turns out is that you can use the same mechanisms. You can use gradient descent to attack them. And in fact, if you look at this problem in general, it's a nonlinear constrained optimization problem. So the easiest algorithm that you can apply to solve this problem is projected gradient descent, which means you start from your input sample, you follow the gradient direction and minimize the function along the gradient direction. If you hit the constraint, like in the figure here, then you project the sample back onto the boundary of the physical domain and you continue optimizing until you reach a local minimum of this function. So that's the basic intuition. And of course, if you consider subprofessor machines and neural networks, you can have differentiable functions in most of the times, and functions that are smooth enough to optimize with this technique. And back in 2013, unfortunately, we did not have any tools, any frameworks to compute the gradients automatically. So what we had to do was computing the gradients by hand. So that's some derivations that we had in the paper, just to give you an idea of the kind of complexity that we faced at that time. So we went back to school and computing derivatives. That's what you need to break these algorithms. And then we implemented these basic attacks. We of course tested that as well also on the popular MNIST and written digit data. And what we found was that you can actually trick this simple MNIST digit recognition process by changing few pixels. So as you can see here, you have a 3 which is misclassified as 7 by just changing few pixels, by applying these small perturbations. So if you want, that was the first sort of the first adversarial attack based on gradient based optimization. Okay, now, so this was the story about how we reach the idea, we got the idea of optimizing attacks against machine learning. Now, for the sake of completeness, and because this field became much more popular since the work by Christian Szegedy and Jan Goodfellow, Intriguing Properties of Neural Networks, I just like to point out how they independently discover adversarial examples or gradient-based attacks against learning algorithms. So I'm sure you know what adversarial examples are, and that, I mean, Szegedy and Goodfellow were the first to apply this sort of attacks to the state-of-the-art image classifiers, like on ImageNet and things. So they deserve the merit of having popularized the field because they attacked a real system which can be placed in production in many different applications. So the idea was just as before, you have an input image, you apply an adversarial perturbation computed by following the gradient of the classifier output or the classification loss, if you wish. And when you sum up the adversarial perturbation to the input image, you have a slightly perturbed image, which is instead classified as a completely different object. So as you see here, the first image is classified as a school bus with a very high confidence, 94%, but the corresponding adversarial example, so the manipulated image, is misclassified as an ostrich with 97% confidence by the neural network. Despite the fact that the output, the adversarial example, looks like the original image to the human eye. So how did they discover this phenomenon? So what they were doing was not trying to bypass classification in a sense, or try to break learning algorithm security tasks, but what they were doing was investigating, in a sense, what networks learned, what the network can learn after the training process. So they were, in a sense, trying to interpret model decisions and so on and so forth. In particular, they were trying to understand at which point a deep neural network changes its prediction on an input sample. And they were expecting to see something like, if you start from a school bus and you want to have it misclassified as an ostrich, you expect that at some point the image is morphed into something different. So the bus should start growing some feather or exhibit some wings, and at some point look like more an ostrich or something in between. But what they instead found was that this process was not happening, and what was happening was just that the school bus was almost the same as the initial image. So they even thought that at the beginning this was a bug, but then they found that this was indeed what was happening without errors. And so the minimum perturbation required to trick this neural net was really, these neural networks was really small, even imperceptible to humans. So that's how they come to the same derivation and the same kind of attacks against machine learning algorithms. So at this point, one may argue that these attacks are very effective because we assume complete knowledge of the target algorithm. So we work in a white box case. That's because to compute the gradient, you need to know all the exact parameter values learned by the classifier, the exact architecture of your deep neural network, and I mean, all these other details have to be known to the attacker. However, back in 2013, we already showed that you can also relax this assumption. In particular, if you assume that the attacker can collect some data, ideally from the same distribution as that used to train your learning algorithm, and potentially he or she can query the target algorithm and observe the decisions, even though this is not always required. At this point, you get, as an attacker, you get a new training data, a new surrogate data with labels that you can use to learn basically a copy of the target model. So this f prime function resembles the original target model, and now what you can do is run your white box attacks against the substitute model, the surrogate model, and try to see if they are said to transfer to the original target model. So if they are successful also against the same target model. So back in 2013, we've shown this on the same kind of learning algorithm, trained on different data sets. And it turned out that we were able to evade detection in most of the cases. And more recently, Nicholas Papernotte has investigated the same idea, but showing that the attack actually can transfer in many cases, even if the target algorithm is different from the surrogate model. So you can transfer attacks from support vector machines to neural networks, and so and I mean you can do you can even attack non-differentiable classifiers. That's the intuition behind this. We have to say that this is not completely and always true, and I mean, if you want to dig a bit deeper into the properties of attacks and attack transferability in particular, we can refer to our recent Usenix paper. It's referred below in the slide. So some quick results on on Android malware detection. So here we apply these gradient-based attacks to manipulate the application file of Android applications. So you have this APK, and the idea was to bypass a system which is called Drebin. It's a very popular Android malware detector based on static code analysis. So you have this Boolean feature representation exactly as it happened for the spam filtering case. You have Boolean features, each representing a different property of the APK file. So for example, whether the application can read or send messages, or it calls some APIs, and so on and so forth. So you have many different features of this kind, and some of them can be injected, some of them can be removed. You know, there are some constraints that can be fulfilled to simulate the attack properly. And we have tested attacks against this classifier in the two different settings, in the white box and in the black box case. And as you can see here in this plot, you have the detection rate against the number of manipulated objects in each APK file, which, let's say, you can consider that we are just injecting new fake permissions or fake API calls into the codes that are never executed at runtime, so they do not compromise the malicious functionality of the code. And what you see here on the y-axis is the detection rate against this number of injected manipulated features. And at the beginning, when you inject 0 features, you have that almost all the malicious samples are detected. So you see that the detection rate is very high, but it decreases very fast as soon as you increase the number of manipulated objects within each application. In the white box case, it decreases very quickly. From 5 to 15 injected objects, the attacker is able to basically evade detection of any malicious sample. And in the black box case, where you have trained a substitute model, you are attacking the substitute model, you observe that you can basically evade detection by injecting more objects, but at the end, you're still able to craft successful adversarial examples against this detector as well. We investigated why this happens, in particular in the case of Android malware. And what happened was that even if you change the learning algorithm, so if you use support vector machines, random forests, and other algorithms, what happens is that the algorithm, even if it's different, at the end of the training process, it tends to find the same relevant features to discriminate between these malicious and benign classes. This means that the classifiers depend significantly on some feature values, on few feature values. So few features, if you want, they are assigned a very high weight in absolute value, which means that whether if you inject this feature or you remove it, you can cause a large change in the classifier output. So the classifier is really sensitive to these feature values. And this, to some extent, explains also why the attack can transfer across different classifiers. So if they tend to depend on a few relevant subset of features, then attacking one or the other doesn't make a big difference. So the attacker is going to manipulate basically the same relevant feature set, and therefore the attack can successfully transfer across different classifiers. So it's the point is that the attack is not different because the classifiers are very similar. So that's the main takeaway here. We have also some more recent development on regarding attacks on executable malware for Windows. Again, some years ago we showed that you can bypass convolutional deep neural networks trained on raw bytes to detect malicious executables. And that's possible by basically optimizing few bytes at the end of the file that again can be injected without compromising the execution, the execution of the malware embedded into the file. So here, for example, it's enough to optimize the choice of the bytes. As you see, the attack algorithm is always speaking more frequently some specific bytes with respect to random selection, and this allows it to evade the target algorithm. And more recently, we have extended these attacks to consider black box attacks, where essentially you do not have access to the gradients of the target algorithm, but you can query it. And here we design an algorithm that optimizes the injection of benign content into each executable file. So in particular, again, if you look at the formulation, the goal is to reduce the confidence assigned to each sample, X. So this value F is the classifier output, assumed to be positive for malicious files. What we do is we extend the initial malware by adding sections extracted from benign files. And we optimize, so for each of these sections, we are not required to copy the entire set of bytes, but we optimize the size the fraction of bytes that we draw from each section. And the size of these bytes that we take is tuned by this hyperparameter lambda. So we are trying to reduce the classifier output, so we are trying to maximize confidence on the benign class while trying to have attaching a small payload to the file, so adding less bytes to the input sample. And we have this constraint subject to Q less or equal than T, which is the maximum number of queries that the attack is allowed to make to the target algorithm. So just to clarify a little bit, so what we have here is two classifiers. One is based on decision trees and the other is a convolutional neural net, respectively on left and right. And what we plot is the confidence, so the probability of being malware against the size of the injected bytes. The dashed red line represents the threshold used by this classifier. So when the lines go below this threshold value, it means that basically all the samples are classified as benign. So you successfully evade detection. We have different curves in each plot representing a different number of iterations of the algorithm. So you can have 20 steps, which is the 20 iterations, which is the orange curve, up to the purple curve, which is 1,000 iterations roughly. And as you see, if you increase the number of queries, number of iterations of the algorithm, what you get is that you can achieve a better trade-off between minimizing confidence and the size of the attack. So ideally, if you increase the number of iterations, you can deceive classification with smaller payloads that you attach to the file. So that's the main takeaway. And I think this is very interesting and explaining also the mechanics of many attacks. So there is always this trade-off between how much you want your sample to be misclassified with a higher confidence on the target class with respect to the number of iterations of the attack and also the size of the perturbation. So that's the values that are playing here. So this is an ongoing work. If you want, you can check more results in the archive link below. Okay, now let's talk about defenses against these attacks. There have been a plethora of work published in trying to counter adversarial examples and detect them, but I think the main successful defenses so far can be categorized in two main different approaches. One is the idea of using robust optimization, so incorporating knowledge of attacks during training to basically push the decision boundary farther away from the input samples, so by increasing the distance that each sample has with respect to the boundary. So that's one line of defense, and we will explain it a little bit better. The other one is to have an explicit class where you detect adversarial examples and place them in. So this is equivalent to the rejection case, where you say, if you have your system with 10 classes, you may have an additional class where the classifier can say for some samples, I don't know which class this sample belongs to, I prefer not to make any decision. Okay, so you have this mechanism of an additional class to enable rejection of anomalous inputs. That's the point. And these two lines of defense can be combined together, so they are complementary in a sense. So as for robust optimization, the basic idea is that you extend the standard classifier training, which is this minimization of the loss on the training points with respect to the classifier parameters, by incorporating attack simulation during the training process, which is this maximum in the inner optimization loop. So what this does is, now we can exemplify this very quickly. So if you take the first problem, you just solve the problem ignoring the max inside. What you have is what you see in the figure. So a classifier that separates your training classes. But now you play the role of the attacker. So we consider a fixed perturbation on each point, like having a hypercube centered on each training point. And within this hypercube, the attacker tries to maximize the loss function by adding a perturbation delta to each sample, which is written in red in the slide. What this inner optimization does is manipulating the training samples to have adversarial examples, basically. And as you can see in the figure, the samples are pushed towards the boundary within the allocated bounded perturbation. And now if you iterate this process, you retrain the classifier on the manipulated samples, and this is what you get. So again, you have now a classifier that can again split the training data. And I mean, you can iterate this process, and there are cases in which you have guarantees of convergence. I mean, it's a minimax problem, so it can be well studied under some assumptions. But the nice property of this problem is that in some cases, you can simplify the problem and get rid of the complex optimization process of adversarial examples during training by basically, so the idea is the following: by basically linearizing the loss function, you can get rid of the inner optimization, so the generation of the adversarial examples, and you can have a regularized problem that is much more efficient to solve, where the key idea is that the kind of regularization term that you have here depends exactly on the kind of noise that you hypothesized to craft the adversarial examples. So the norm of the regularizers that you see there depends on the norm of the noise, whether you have an L2 noise or an L1 noise or L infinity noise. You can adjust the norm of the regularizer accordingly. And this was very interesting when we saw that, and we decided to apply it to the case of malware that we discussed before. So it turned out that the optimal regularizer against these Android malware attacks was to take this infinity norm regularization on the weights of the SVM, which led us to develop this SEC SVM, so the secure SVM we call that. It's also known as infinity norm SVM. So in this case, as you can see, if you compare the curves, now remember the green one is the one that we commented before. The blue one is an heuristic defense based on assembling classifiers. So you combine classifiers to try to get some more robustness. But the best classifiers are the red lines, which are exactly those using this regularizer that I just described. And you see that to break these algorithms now you need to manipulate much more features than in the previous cases, because the red curves decrease more gracefully than the other ones. So that explains that you need to apply larger perturbations to bypass detection in that case. And the intuition is that this kind of regularizer, basically, the practical intuition behind robustness here is that this regularizer bounds the weight values, the absolute weight values. So now we are basically de-emphasizing features. There can no longer be features that are assigned a very high relevance towards making decisions, but now, I mean, all the features tend to be equally weighted in each decision. And so it should be clear that for an attacker to bypass detection now, I mean, he is required to change more features to have the same decrease in the classification output. So that's the basic intuition behind this attack. And what all these techniques of matching the regularizer to the kind of noise that you assume for adversarial examples, or playing adversarial training, what they do is basically they tend to push the decision boundaries away from the input samples. So what you're doing is basically learning smoother functions with respect to the specific kind of worst case noise that you assume on your data. And this is, I like this figure because I think it conveys in a very clear way the intuition behind. So you can see that on the right plots you have a much smoother function both against random perturbation and adversarial perturbations. So the net effect is that you push the boundary farther away from the input points. So you have a better regularization strategy for your model. So that's why these strategies increase robustness against adversarial examples. But as I said, if you want to do something more, you can now apply rejection. Just a quick note on adversarial training, just to tell you that it's, again, the very first examples of adversarial training date back to the 2004 paper. So that's the first paper on adversarial classification, to the best of my knowledge, and they have a sort of simulation of game between the attacker and the defender in that paper, even though it's not formalized as a min-max game. The first min-max formalization of the adversarial game, if you want, is described in this paper in ICML 2006, Nightmare at Test Time, by Globerson and Rovey, so if you're interested. But I mean, the most elegant formulation that I've seen so far is the one provided by Michael Bruckner and Tobias Schäfer in their works on static prediction games for adversarial learning. So there's this JMLR paper, and the whole PhD thesis by Michael Bruckner deals with this formalization of games. So you have adversarial learning is formalized as a game theoretical framework, and it's not only a minimax game for the robust case, but you can also have different kind of games by relaxing the assumptions either on the classifier or on the attacker. So if you want to have, if you want to know a bit more on adversarial training outside of the deep learning community, just refer to these papers. I think they have nice examples. They also studied convergence and under convexity assumptions of the learning problem. So I think it's very interesting to have a look at it. I was talking about the other line of defenses, so detecting and rejecting adversarial examples. This technique is basically based on the idea that the classifier should not be obliged to make a decision on every point in the feature space, as you see here, but rather than saying always the point is red or blue, the classifier should be able sometimes to say, I don't know, especially if the sample that is going to be classified is very far away from the training classes. So in that case, by restricting the decision regions around known classes, you may somehow prevent the problem of adversarial examples. And we exploit this. We had a couple of papers on this topic, but similar ideas appear also on other papers. So what you can do basically to detect these anomalies, these anomalous inputs, is to check what happens at different layers in neural networks, because you expect that at some point the adversarial examples can exhibit an anomalous behavior at some intermediate representations. So by building on this idea, you can somehow mitigate some of the attacks, but it turns out that if the attacker knows how your detection mechanism is implemented and he has, well, let's say, white box access to it, he this mechanism can be broken anyway. And this is an important comment to make, because evaluating the security and the robustness of this algorithm is a serious problem. So we should always be aware of the fact that the attackers can be adaptive, and they can always evolve to break or bypass your defense. So testing against known or previous attacks gives basically no robustness and no guarantees that your classifier is robust against adversarial examples. But we as designers of machine learning systems should always be proactive. So always try to test our system against a stronger possible attacker that exploits knowledge of the defense. So we have to test the security, the robustness of the system against the worst case. And despite the attempts towards formal verification or network certification, robustness certification, there's no way of efficiently and formally verify the robustness of a network. So we are left with empirical techniques, and in this case, we have to try. That's why we have to try to do our best, because we have to try to design an algorithm which is able to try to break your defense in the worst case for the defender. Just to give you a short remark on this part, I just want to tell that many of the proposed defenses some years ago were claiming to be robust against adversarial examples, claiming to almost have solved the problem. And what instead turned out is that, and this was shown by Nicolas Carlini and David Wagner and Anish Attali in these referred papers, was that the defense was not really effective in defending against the adversarial examples, but it was just obfuscating the gradients. So if you have a complex function which is not smooth, it's clear that if you run a gradient-based attack against it, the attack is not going to find a good optimum for your problem. So it may easily get stuck in a local minimum that does not allow to evade detection, does not allow evading detection. And so what these authors did 2 years ago basically was to find smoother approximations of the defense algorithms and now run the attacks using these approximations. So by smoothing the function or the gradient, now you find again a useful signal towards evading detection. And so all these defenses were basically shown to be flawed and not to be correctly evaluated against adaptive attacks that knows how the defense mechanism is implemented and exploit this mechanism to bypass detection. Okay, so now after we covered extensively evasion attacks and defense mechanisms, I'd like to talk a bit more about other attacks against AI and machine learning. And if you're interested, we have a complete taxonomy in the paper Wild Patterns, referred below in the slide. And here you can observe that you have many other different possibilities of attacking machine learning algorithms. We have discussed evasion attacks, which are manipulation of test samples to break integrity of a classifier, so to obtain misclassifications that do not compromise normal system operation. But you can also have attacks towards causing denial of service, for example, for legitimate users. That's targeting availability, or even breaking privacy and confidentiality of the algorithm or its users. You can have attacks trying to steal the models which are served as web services, for example. You can try to recover some of the training samples that are used during learning, possibly uncovering private information, private and confidential information about the system users. Or you can have other attacks staged at training time. One interesting thing is that regarding manipulation of test data, you can also cause availability problems. So in the empty cell there, there's actually a couple of attacks that can be mentioned. So I was just contacted yesterday by Professor Ross Anderson from Cambridge, and they have developed recently what they call a sponge attack, which is an attack that basically manipulates the test samples in a way that neural networks consume more require more energy to run, so eventually causing a denial of service for legitimate users. So that's very interesting. So you can check it out on the archive. Reprint is available. But now I just want to talk about other training attacks staged at training time to cause denial of service. So that's what we call DOS poisoning, and it's what we developed in the 2012, and that was actually the first gradient-based attack against learning algorithms. So the idea here is to find a training point that compromises classification on clean test data, which is not touched by the attacker. So let's say, for example, you have a classifier, an SVM that separates these two classes with a small error. If you add a red point in the bottom right corner, you see that the boundary tilts a little bit, and then the clean data, so another bunch of test points without attacks, sampled from the same distribution, is misclassified with an error of 4%, almost 4%. Now the question is where to place this point xc to cause the maximum damage for the classifier, so the maximum classification error on the other clean samples. And so if you take xc and you repeat this process on every possible location of the attack point, well, that's what you have, and this is how your objective now looks like. So this is the function we would like to optimize to find the best attack point in the training set. And as you see, the best location is the red area on the bottom right corner, where the error on the clean data can increase up to 6%. But now, I mean, this was just an heuristic explanation of how the attack should work, how the attack works. But this can be formalized, and in particular it's formalized as a bi-level optimization problem, where the attacker tries to maximize a loss function on clean data, but it does with respect to the training point, to a training point. And of course here the constraint is the learning problem itself, so the fact that you retrain the classifier on the attack points, or on the attack point in this case. So that's why it's a bi-level problem, because you have an outer optimization, and again, the constraint is itself an optimization problem. So it's a bi-level optimization in the end. Now, the bad news is that the gradient is not as easy to compute as in the evasion case, because the classifier is changing here while you modify the training data. But the good news is that there are some tricks that you can borrow from optimization to solve this problem. In particular, you can replace the inner constraints with the equilibrium conditions, and then you can compute the gradient in closed form, so that you can again run the attack as a gradient ascent process in this case too. And here you have some examples on 2D on a 2D problem, but we also of course have one nice example on the MNIST handwritten digits. And here you see that we have one classifier trained on 100 digits to discriminate between 4s and 0s, so it's just a two-class problem. And now if you take the digit image on the left, which is a 4, and you just flip the label, well, nothing happens. I mean, the error increases up to less than 1%, I think, on the clean testing samples. But then if you take this 4 labeled as 0 and you optimize it using our attack, you get this blurred image that you see in the middle, which is a 4, and it somehow resembles a 0 in the background. And now by just adding this sample labeled as 0 along with the other 100 training points, if you do that, what you get is that the classifier now, the test error now goes above 20%. And with a single sample. So basically a single sample controlling less than 1% of the training points in this case allowed the attacker to completely screw up the classifier also for legitimate users. So that was a very quick overview of poisoning attacks, denial of service poisoning attacks, and there are countermeasures against them, and they are all based on the fact that poisoning samples have to be outliers in some sense, because if you want to drift the training process, if you want to poison your classifier to learn a different data distribution, you cannot add samples coming from the same distribution. So they have to be outliers, otherwise they would have only little impact on misleading the training process. And so the defenses are based on either sanitizing the data, so finding the outliers and removing them, or having robust learning processes that basically know that a fraction of the samples can be outliers and try to exclude them from training. If you're interested in knowing more, I just give you the reference to this paper where we developed a very effective defense in detecting poisoning samples for regression tasks. But here again, this algorithm called TRIM is very simple. So the idea is to iteratively identify a fraction of outliers in your training set, which are points assigned a very high loss value during training, and iteratively remove them from the training set. And eventually this procedure is able to learn more or less the original function that you observed on the clean data. Modulo some differences, of course, depending on the fraction of outliers that you have, of poisoning samples in your data, of course. So just to conclude very quickly, I just want to tell you why AI is vulnerable, and I will do that by using not exactly my own words, but using words by Bernard Scholkopf. And so all the problems here are based on the fact that machine learning has this very strong underlying assumption that the data that you use for training is representative enough of data that you will see in the future. That's called the IID assumption. That means your problem is stationary. Data is independently and identically distributed. And of course, this assumption is easily violated in the real world because, I mean, you cannot forecast all the cases that you will see when an agent is free to walk around, or like a self-driving car going on the street, and so on and so forth. And so the success that we have observed so far for image classifiers, speech recognition, and all these tasks is based on the fact that we have collected very large data sets which are quite representative of the images and audio that we are using every day under normal conditions. But of course, I mean, the fact that you are not able to, we cannot do this basically for all existing tasks. Like if you have a robot that explores the world outside, you cannot basically envision all the possible cases that it will encounter in the real world. So the IID assumption, or if you have also a problem in which data evolves over time, like malware detection, or all these problems with an intrinsic adversarial nature, I mean, in those cases, the stationarity assumption, the IID assumption, is clearly violated. And adversarial attacks are just, I mean, the clearest violation to this hypothesis, right? So they point exactly at the lack of robustness that comes from this IID specialization. So that's basically why. So machine learning is vulnerable just because it was meant to operate in a stationary environment, and we are testing it under non-stationary conditions and adaptive attacks. So that's not really what it was meant to work with. Okay, just a few more words. If you're interested in these historical remarks that we have discussed throughout these talks, please just have a look at the paper. You can also see this nice timeline, which is one of the figures in the paper, and then you have all the references there if you want to rebuild the history of adversarial machine learning since the earliest work on this field, before the deep learning the attacks on deep learning came to the stage. All the attacks and algorithms that I've described are included in our library. It's called SecML. It's a library you can use to simulate attacks against learning algorithms, including supercomputer machines, neural nets, and deep learning frameworks. We also have some explanation methods to understand when attacks work and why, and many other features. So if you're interested, you can check it out, and you're welcome to contribute in case you want. And finally, I'd like to thank you for listening all the talk, and also thank to all my collaborators. I mean, most of the work is also their own merit. Okay, I'm open to questions now. Thank you very much.